Hello everyone, welcome to this lecture. So we're now going to look at situations where you have slightly more complicated forms for the equation. So far we saw just two equations, two variables. We seem to have a good control on how to go about solving that. Let's push a little bit further. We'll look at cases where you have maybe three variables and three equations, right? So 2 and 2 we have already done. We have not done two variables, three equations, three variables, two equations, and three variables, three equations. Okay, we're going to see that one step after the other, how to go about solving it. Once again, our approach will be very similar to before. What is our approach? You take a new problem, how do we attack it? I do something to convert it into an old problem or a very easy version of the problem that I can solve. Okay, so that's the same principle that's pretty much used everywhere in mathematics and many other problem solving areas. So we'll use that same principle over and over again. So if I have three variables, I know how to solve two equations, two variables. So if I have situations where there are more variables or more equations, what will I try to do? I will try to reduce it to a case I know. Okay, so that will be the general principle, and let's see how that applies in each of these scenarios. It will give us some clear ideas on how to proceed. Okay, so here is this two variables, three equations case. Okay, I've drawn two things. I've written down two things here. One is this so-called equation view. There are two variables, three equations, and notice how the notation for the coefficients have changed, and notation for the variables also have changed. Okay, instead of saying x, y, a, b, c, etc., I am doing some indices here with numbers. First thing I am doing is the variables, I am making them as x1, x2, x3, so on. There are only two variables here, so I have only x1, x2. So if I have three variables, I will write x1, x2, x3, so on. If I have even 10 variables, I can write x1, x2, x3, x4, x5 till x10. Now, if I have any other notation, you see the difficulty, right? This 1, 2, 3 nicely solves the problem for me. Otherwise, I'll have to know x, y, z, w, then what? If I have 10 variables, I'm a little stuck, isn't it? So that is a very nice way to get rid of this problem of notation. So our variables will be always x1, x2, x3, so on. Okay, in a real problem, it may be v1, v2, v3. If it's voltages, it may be something else, but that doesn't matter. It's just a notation. Okay, for problem solving, for general notation, I will use this x1, x2, so on. Notice what I've done with the coefficients. I've done something a little bit more careful here. The coefficients I've written down for the first equation, it's a11, a12, b1, right? So a11 multiplies x1, a12 multiplies x2, and then b1 is on the right hand side. Okay, so I have a11 x1 plus a12 x2 equals b1. Likewise, I have done here for a21 also, a21 x1 plus a22 x2 equals b2, and a31 x1 plus a32 x2 equals b3. So this coefficients is basically like aij, right? The coefficient is going to be aij. I is the row and j is the column. Okay, so you see that is the notation here. It's sort of like a matrix notation. That's for these coefficients aij. Once again, this nicely solves the problem for me. I don't have to keep looking for a, b, c and all that. I always write aij, the ith row, jth column, right? And then so now that's on the equation side. The same thing can be captured very conveniently in matrix form here. Notice what I've done here. I've put all the coefficients on the left hand side together on one side, and I put this sort of like this dotted line to separate it from the coefficients on the right hand side. Okay, so the coefficients on the left hand side make up a 3 by 2 matrix, right? So this is 3 by 2, and then the right hand side coefficients come as one column. Okay, so it's overall a 3 by 3 matrix, but then I cannot, I have to separate the left hand side and right hand side. So I put a line here to show that separation, and then I have 3 rows and 2 columns for these coefficients, just conveniently capturing the coefficients in a matrix. Okay, so I hope this is clear. So I have 3 equations, 3 linear equations in 2 variables. Okay, so what is going to be my attempt? My attempt is always going to be to try and eliminate x1, and I will assume this a11 is not equal to 0. So I have been making these assumptions on not 0, etc. Later on we will see what to do if they end up being 0, right? So it's a legitimate question. I'm sure you have it. We will deal with that later in examples and all that. I'll show you. It's very easy to handle that situation. It's just a special situation. So, most commonly you can assume a11 is not equal to 0. Okay. So, when you do that, you can start eliminating x1. So, we have done this before, right? There are two equations you can eliminate. So, I will do that repeatedly, right? I will take the second equation and eliminate x1 between the second equation and the first equation. That is what I have done here, right? And I will take the third equation and once again eliminate x1 between that. So, what exactly have I done here? I have done equation 2, you replaced it with equation 2 minus a21 by a11 times equation 1. Okay, so that is what has happened here. So, the first equation got multiplied by a21 by a11 and then I subtracted this from the second equation, I subtracted the product. So, that is what I did. The same thing, and we have done this before with two equations, so hopefully so this is easier for you to see. So, I got x1 eliminated, I got an equation only in x2, a22 minus a12 a21 by a11 times x2 equals b2 minus b1 a21 by a11. Is that okay? So, you see how I got this equation, that equation is clear. Now, for the third equation, I do the same thing. Instead of equation 2, it is going to be equation 3 getting replaced with equation 3 minus a31 by a11 times equation 1. Okay, so that is what is done there. Let me write that down. Equation 3 got replaced with equation 3 minus a31 by a11 times equation 1. Okay, so that got replaced and you got one more equation. So, you see what I have done here, I hope you can see that. I have got rid of x1 in the second equation and in the third equation. I am able to eliminate x1 repeatedly using the same idea. So, I have captured that in matrix form here for you to see a little bit more clearly. So, I have the first equation a11, a12, b1, right, that is there. The second equation has a 0 in the first place and then it has this slightly more complicated algebra going on here, but not that complicated, simple enough to see that. Okay. So, what do we do now? Now, it's not too bad to proceed from here, right. So, you can do this in a reasonable way. I have two equations for one variable x2, right. I have to solve for x2. I know how to do that. I have only one variable, one equation, I know how to solve. There is no x1 here. So, I can solve for x2. Once I solve for x2, I can go back and solve for x1. Okay. So, I am going to show you how this is done with a few examples. Instead of using complex notation and trying all sorts of cases, we are going to see some examples and see how this works out. How do these two equations in one variable, how they work out, what are the different types of cases that are possible and how it works, etc. But in principle, we know how to solve this. We have seen this before, right? When you had two equations with just one variable, there has to be some consistency and all that. Otherwise, you won't have a solution. All of that will play a role here. But this is the basic idea. Once again, I want you to think about what we have done here. We have taken a new problem and broken it down into a problem that we knew already. And you solve that part and then go back and plug it in and get the solution to the new problem. Okay, so same principle. Let's see a few examples. The first example is given here, x1 plus x2 equals 1. Let me write it down for you here. Just make sure I get that right. 2x2 is 2, 2x1 plus 3x2, I think that's 4, right? Yeah. Okay, so let's capture this in matrix form. 1, 1, 1, 2, 2, 3, and then there is this dotted line, then you have 1, 2, 4. Okay. What's going to be my elimination step? Equation 2, so we can write this as 1, 2, 3. It's going to be, I'm just writing it in laborious detail for the first time. After that, I will be a little bit faster. Equation 2 minus 1 by 1, right? So, that's just equation 1, and then equation 3 is going to be replaced with equation 3 minus 2 by 1 times equation 1. Same way here, row 2 is going to get replaced with row 2 minus 1 by 1 row 1, just minus 1 times this, and then row 3 is going to get replaced with row 3 minus 2 by 1 times row 1. So this is what's going to happen in the elimination step. So now if you do that, you'll see that the equations become, the first equation is retained, x1 plus x2 is 1, second equation is just x2 equals 1, and the third equation simply becomes x2 equals 2. Okay. So you can write it out here as well, 1 1, the dotted line 1 1 1, 0 1 1, and then 0 1 2. Smaller dotted lines, it's getting mixed up with 1. So this is what I've got here, but notice what we have, look at this guy, right? Now I have to try and solve for x2, but guess what? x2 has to be 1, x2 also has to be 2. So this is a contradiction. We have seen this before, we got these contradictions before. So anytime you have a contradiction, what does that mean? There is no solution. Okay. So we have not yet seen the matrix part of it yet, but we don't need to bother about it. But we've seen here already that there is an inconsistency. When you have two equations in x2, they have to be consistent. Otherwise, there will be no solution here. So this is a case that's going to correspond to a no solution. x1 plus x2 is 1, x1 plus 2x2 is 2, 2x1 plus 3x2 is 4. There can be no solution to these three equations simultaneously. No value of x1 and x2 will satisfy this. So it turns out, because there is only two variables, I can picture this on the xy plane. Each of these equations, if I think of x1 as x and x2 as y, it becomes a straight line, right? X plus y equals 1 is a straight line, x plus 2y equals 2 is a straight line, 2x plus 3y equals 4 is a straight line. And if you end up plotting it, here is a plot. You see that there is a red line, there is a blue line and a green line. Each of these lines represent the three equations that you have here. And you see all three of them are not collinear. All three of them are not passing through any common point. Any two of them are intersecting, right? Blue and red are intersecting at one point, blue and green are intersecting at one point, green and red are intersecting at one point. But all three of them are not intersecting at the same point. Okay, so there's no solution. So this is a graphic visualization of what's going on. But through elimination, we saw that there was no solution. Okay, so that's the problem, the first problem, and that was solved in a very simple way. Hopefully you saw that. Okay, the next one is very similar, except the third equation becomes 3x1 plus 4x2 equals 4. So let's try and solve that. The second problem is x1 plus x2 equals 1, x1 plus 2x2 equals 2, 3x1 plus 4x2 equals 4. Okay. So we're going to repeat the same step, but I'll do it a bit faster. Maybe the matrix form is not so important here, but anyway, we'll carry it along just for you to see how it's going to look. Right. So the elimination, I'm going to do equation 2 is equation 2 minus equation 1, so on. So maybe I'll write it down here, 1, 2, 3. This alone, I'll write down very quickly, equation 2 minus equation 1, and then equation 3 minus 3 times 3 by 1 times equation 1. Okay. So this is what's going to happen here. So the first equation is retained, x1 plus x2 is 1, and then equation 2 minus equation 1 gives you x2 equals 1, equation 2 minus 3 times equation 1 is going to give you x2 equals 1 as well. Okay. So wonderfully well, we've got the solution here, and that ends up being consistent, right? So it is consistent. X2 equals 1 is your solution. So now once you put x2 equals 1, this will give you, if I use this equation, it immediately gives you x1 equals 1, x1 equals 0, I'm sorry, right. You put x2 equals 1 here, you're going to get x1 equals 0. Okay, so notice how this equation got solved. We again used the same process, but we got these two equations for x2 and they were consistent. There was no contradiction here. x2 equals 1, x2 equals 1. So I was okay. I didn't get a situation like here where it ended up being contradiction and there was no solution. Here there was no contradiction, it's all consistent, and I got x2 equals 1, x1 equals 0. So the solution is 0, 1, and it's unique. Right, it's a unique solution. There's only one solution. There's not more than one solution. Okay, so if you want to picture this on the graph, because this is two variables, we can do that. It turns out in this case, the three lines actually pass through one common point, right? 0, 1, which is what we saw, and this gives you one unique solution. Okay, so this is the second example, an interesting example. You can contrast it with the previous example. You see how this situation varies. The third one is very simple again, but let's just go through that because it illustrates another situation that can happen. Again, you have x1 plus 2x2 equals 1, 2x1 plus 4x2 equals 2, and then 3x1 plus 6x2 equals 3. I think these are the three equations. And let's just blindly follow our elimination method. Maybe you've seen this before, or maybe you can quickly see what's going to happen here. But if you do the elimination, I'm going to be very succinct here. I'm not going to write what the step is. Okay, mentally we'll do. It's going to be equation 2 minus 2 times equation 1, right? So that will be 0 equals 0. You can check that. Okay, equation 2 minus 2 times equation 1. You get 2x1 minus 2x1, 4x2 minus 4x2, that also will cancel, 2 minus 2 will cancel. Likewise, I am going to do equation 3 minus 3 times equation 1, right? Again, you will get 0 equals 0. Okay. So this guy is all automatically satisfied. So you are left with only one equation in two variables. Okay. What is that? This will give you infinitely many solutions, right? I've not written the matrix form here, it's not so relevant. Infinitely many solutions. So we can write the parametric form. You put x2 equals u, I'm going to get x1 equals 1 minus 2u, right? If I put x2 equals u, I'm going to get x1 equals 1 minus 2u. So the solution is of the form 1 minus 2u comma u for all u in the real line, right? So for any u in the real line, you will get it. If you want, you can write the solution in matrix form. So this is basically 1 minus 2u, that's going to be minus 2, 1 times u plus 1, 0. Okay, so this is like the matrix form of the solution. We've seen this before, how to write this down, right? So we see here in this interesting case, even though you have three equations, there is actually only one equation. The other two are just the same thing multiplied by 2 and multiplied by 3. I'm just not done anything different here. So basically what happens in this case graphically is all these three lines are on top of each other. They are the straight line. So if you want to solve it, you get infinitely many solutions. Okay, and you can express this in that sum of two vectors form, line plus a point on the line plus a line through the origin form. You get all those answers as well. So hopefully you see that how to write it in this parameterized form, this infinitely many solutions. Okay, so basically I want to conclude by saying this, if you have two variables, three equations, all sorts of solutions are possible. You may have no solution, you may have one solution, unique solution, you may also have infinitely many solutions, and everything comes from the elimination process. It was very simple, right? You started with elimination and you can quickly identify what are the various things that can happen. You may get unique consistent equation, you may get contradiction, or you may just get 0 equals 0, in which case you get infinitely many solutions. Okay, this is the end of this lecture. We'll move on from here to the next possible cases where you have maybe 3 variables, 2 equations, 3 variables, 3 equations, and so on. Okay, thank you very much.